Is it time?
Just keep playing, Kim.
Oh, they want me to keep playing. Okay, we'll do a new piece.
Thank you.
Sure. Okay. You still want me playing? Let's see.
Yes, please.
Is there more you need?
Yes, if you can, until we interrupt you, please type.
Okay. You ready for me to start your slide?
No, not yet. I'll let you know.
Okay, I'm gonna
I'm trying to get a
go
hold of it.
back to my river. Oops. I'll do a clear de lune.
Thank you, Kim.
Anytime. Let's see, clear de lune. Okay. Okay, wait.
Okay, Kim, can you hear us?
Great.
Thank you very much for playing such an extended time while the
Thank
crew on the
you.
ground were figuring
Absolutely.
out problems.
Thank you so much for having me.
Barb, thank you very much. Kim, thank you very much. I also hear that some people, hello?
Can you hear me?
Yes, Barbara, the floor is all
thank you so
yours to
much.
start the meeting.
Okay. I'm not sure where our camera is at this point.
You're looking at it, yep.
Well, I may be a blind spot for a moment. Well, welcome everybody to our April OCA general meeting. I'm sorry for the delay. We've been having a few technical difficulties, but it's great that everybody is still here and ready to enjoy a very informative as well as entertaining evening. And given that it is so late, I will not prolong matters, but we'll turn matters over to Kyle to give us the club announcements.
All right, here we go. Right, welcome new members. If you're there in person, your name badges, when they're available, will be on the whiteboard. If you're attending online, eventually in a couple months, those will be mailed out to you. Everyone in person, remember that coffee, donuts, and water are up available for purchase for $1 each up by the entrance. The next Ancestar party is April 26th. The next astrophysics special interest group meeting will be on April 18th at Orange Coast College. Astroimaging May 2nd, as well as the beginners classes that day online. And the next board meeting is May 4th. You can find more information about all the upcoming club events on the website. Doug's trip out to the Owens Valley Radio Observatory is scheduled for June 20th and June 21st. It's always a very fun time. If you'd like to attend, there's no cost to it, but reach out to Doug Millar to reserve your space. The club's Adopt Scope program is up and running. You can see here how to get to the information about the program on the website. You can download a sample adoption agreement and look at the sample inventory of what's currently available, along with more information about the program if you're interested. Our outreach events coordinator is Martin Christensen, and reach out to him if you are able to help with any of these upcoming outreach events. They're always a fun time, and we would love to have some help with those. Serious Astronomer newsletter. If you have any items of interest, please contact Dave Fisher. We always like to get submissions from club members for items to put in the newsletter, and he'll review those items of interest. Friendly reminder to all those using the ANSA site to lock up the ANSA house if you're the last one to leave the site, ensure all the windows are closed, and close the gate to the site. Additionally, we'd always like everyone's help with weed clearing to ensure the site stays safe for everyone. The next general meeting will be May 9th, and I'll turn it over to Chris Butler for the What's Up presentation. Thank you.
All right, where's the button I push? I'm already on, and up and down on the arrow keys, just advance, retreat. Oh,
Yeah,
all
the
right.
slides are not shared yet.
Oh, they're working on it. Okay. Are we shared and everything?
Yes, great.
Oh, very
We
good.
see it.
All right. Well, welcome to the What's Up portion of the program, where I guarantee nothing really is going to go wrong, because today is the anniversary of the Titanic's last sailing it ever did from Ireland, actually. So yeah, that's the good luck that we're all counting on. Can I? Yeah, we're good. Let's actually try a button. See what happens. Nothing happened. No, I mean, nothing bad happened. It's just not. I did the down button. I did the up button. You know, the thing I enjoyed the most was that everybody got to see most of my slides in advance. So there's like zero suspense for any of you. Although I really should have changed out the presentation to a completely different one when you weren't looking, just to keep things fresh. Okay. All right. I bragged. Yeah. What's that? Wait, something. We. What? Oh, apparently there's. Sure.
Apparently, the Neanderthals and the Homo sapiens got together and produced no discernible offspring. Tonight, the Apple and the Microsoft got together, and I predict there will be no discernible offspring.
Okay. So can slowly. All right, here we go. Let's see what happens, ladies and gentlemen. No, it's not live from Anza. Hey, this is a different slide, and I'll take it. The point of this slide would be full moon's tomorrow. So you don't like the moon? You're out of luck. For the next couple of days, we're going to have a bright full moon, and then toward the we're going to be talking about this one for years. All right. The sky, ladies and gentlemen. Oh, sure I do. Yeah, it's working again in the same way Lucy is holding out the football. Okay, I'm ready. No, let's do it. Don't. See? Other astronomy clubs don't have meetings like this. All right, good enough. This is a rundown of what's going on with the planets. The important thing to note is that most of them are not around for us to look at right now. Really, only Mars and Jupiter. Got a picture for you in just a second to explain why. Okay, down we go. All right, as far as the sun, you can see we're getting longer days and shorter nights now. We're past the vernal equinox, building up towards eventually summer arriving in June. That is, unless we have technical problems. Next picture, please. Here's the important one. Daytime view as if you could see the stars. There's the sun. Look how many of the planets are gathered in this part of the sky. You've got Uranus over on your screen left. The sun is there in the center. But a whole gaggle of them. This is in the morning sky. We've got Mercury, Neptune, Saturn, Venus, all of these things, and even the dwarf planet Ceres thrown in there, the World Series. The idea being that the news media will pretend this means something, and they'll make some kind of a big story about the planets all being aligned. What it really means is that they're in the same part of the sky as the sun right now, so most of them just aren't available to look at. Next picture, please. Shame with Saturn. You saw this slide before. The rings are edge onto us right now. The actual date of the ring plane crossing is labeled there for you. Unfortunately, when Saturn will crawl out in the morning sky and get farther away from the sun, we'll be able to see Saturn, but the rings won't be quite so edge on this time. It's just kind of bad luck that we don't get to see this unusual event this time. Next picture. Looking at the wide picture of the sky as far as stars when the evening first starts, we have wintertime stars like Sirius there and Capella that are still over in the western part of the sky. They are getting lower, though. You're losing your chance to see them. High overhead, we've got Regulus, and that's kind of the beginning of the proper springtime stars. And then we've got Spica and Arcturus rising in the east. So it is definitely springtime now in the sky. Next picture, please. All of the really, really bright stars that are in the winter sky will be over in this area, which is circled, the winter hexagon. Orion is there, a whole bunch of wonderful things. But if you love those, catch them at 9 o'clock at night like this. It's just gotten really good and dark, but they're definitely setting into the west. So last call for winter. Next picture, please. I promised planets. We do have Jupiter, brilliant in the west as evening gets good and dark, but notice it is on its way down. So Jupiter, again, kind of last call for Jupiter. Mars is still well placed in the sense that it's well above the horizon. It's up high in Gemini. However, we have already passed Mars, and Mars is now only about 7.5 arc seconds across in your telescope. When we pass Mars, we get a much better look at it than we do most of the time, and it has shrunk quite a bit. It's still naked eye bright. You'll notice it up there with the two stars of the Gemini twins. And then that third object there, that is Mars. But through a telescope, it has shrunk quite a bit. And then, of course, now tonight, we have the moon almost entirely full, rising in the east right now. Next picture, please. If we go on towards midnight, these are the stars that are exactly opposite the sun in the sky. They are theoretically the best to look at. They are up the longest in a dark sky. You can see Jupiter by this hour is actually setting. Mars is well on its way to setting. And then the moon will, of course, be flooding this part of the sky with its light. But it'll get out of the way in a week or two. And this is the part of the sky we'll talk about in more detail in a moment. But first, for those of you who are up all night, next picture, please. Oh, ooh, tap you on the shoulder when I want to change a slide. No, yeah, no. Oh, hey, no, this is great. We got it all figured out. It's a whole new system. It's still on the midnight hour here. I circled the most famous of the springtime constellations, and by midnight, they're all like right overhead. In the orange kind of circle is Leo the Lion. Leo, very famous. Then in green, the Big Dipper, part of course, Ursa Major, the Great Bear, that's almost straight overhead. The purple circle has Boötes, the herdsman in it with bright star Arcturus in it. And then down in the south, we've got Virgo, the maiden in the pinkish type circle. Next picture, please. I promised to look at the 5 a.m. pre-dawn sky. Sky's already starting to get light if you're up at ODark 30. Remember I mentioned all those other planets that were crowding over there near the sun? Well, if you look on the horizon there out toward the west, or the east in this diagram, pardon me, the east, you see Venus, brilliant down there. It has just emerged into the morning sky. It's a crescent right now in your telescope, by the way, 49 arc seconds across tonight, I believe. It's a large crescent. So you could find out, even pair of binoculars, good binoculars, you might be able to see it as a tiny, tiny little crescent, certainly in a telescope. But all those other planets are buried down there too. Mercury, Saturn, all the rest of those, even lower in the pre-dawn murk. Next picture, please. This is the constellation I wanted to talk about tonight, which is Hydra, Hydra the water snake. And you see it here as it would be at midnight. It is directly opposite the sun. I like it because it looks like the duodenum. I promised somebody I would actually get the word duodenum in to the presentation. I've never used that before. It actually looks like something you'd find in the cat box more than a constellation. It is one of the long stringy constellations, which really is kind of cheating. There's an empty spot and we just drew a line. It is one of the ancient constellations, going all the way back to Ptolemy. However, interesting thing about it is that it is the largest of the constellations, I believe, in surface area. It is not the tallest north to south, I know, but certainly east to west. It's so long that when the evening first starts getting dark, only the head has risen and the tail is not up yet. So you have to wait for a while until about midnight, all of it's well clear. Next picture, please. As I mentioned, this is one of the ancient constellations. It is surrounded by a whole bunch of neighbors, some of which in this 1825 illustration no longer exist. They are not recognized constellations. If you look, you'll see a cat in the left part of the illustration. That is Felis, not Felix, but Felis with an S. The cat, that is no longer an allowed constellation. Some of the other ones, the angle bar looking instrument there, of course, is a sextant, a navigational instrument. Sextants, they're guaranteed to get giggles from school groups, is there. We have Antlia, the water pump, is down in the kind of the bottom curve of the snake. We have Crater, the cup, which is another ancient constellation for a ceremonial cup. By the way, that's why the holes on the moon are named crater for your Latin, is because they are bowl shapes, right? So that it actually does make sense. Corvus the crow is a very bright and obvious pattern. You'll see it in stars in a minute, but you see it there on the drawing. And then lastly, and sadly, perched on the tail of Hydra is Noctua the night owl. Noctua was deleted as a constellation, so it no longer exists. The stars, however, stubbornly remain. Next picture, please. Here's the modern view of the constellation, drawn up by the International Astronomical Union, the same people that killed Pluto. So what do they know? However, this is a modern chart, and we'll be taking a brief tour down the enormous length of Hydra here, and I'll show you 4 of my favorite objects to look for along its snaky length. Next picture, please. They are color-coded there. I use yellow for star clusters, green for planetary nebulae, as they are called, and then red for galaxies. That's just my convention. But you can see here this long, long pattern. There's one bright star that I've called out. It's not a first-rate star, a second-rate star, Alphard. Distinctly orange star, which marks the heart of Hydra. There's also a really cool pattern up at the top. You can see this kind of a knot of stars over in the far west part, northwest part of the constellation. And there's a star in particular I'm going to refer you to up there to look at. Next picture, please. Let's start up in the north here. That star, which I did not know the name of until just recently here, it's Epsilon Hydri. I knew it that way. But Ashlesha is the name of that star. It has a proper name. It is a wonderful multiple star. And some of the components are very close together in a challenge for amateur instruments. So Epsilon Hydri up there at the top in the head, well worth looking at. And you see Alphard there. You also see M48. M48 is an open star cluster, which is in the far west, just a little bit below the bright star Procyon, over in that part of the constellation. And then we also will be referring you to the planetary nebula at the other end in a moment. I'm looking to see what I can see. Cool. All right. Next picture, please. Here's a picture of M48, about the size of the full moon, easily seen in binoculars, and actually a pretty treat in telescopes, although it isn't visited as often. It will resist you moving your telescope off of it because they're really lonely over there. They like having somebody visit. You try to get your telescope off, they'll be saying, wait, I was going to make espresso. So definitely do visit them. Next picture, please. Here we go. NGC 3242 in Hydra. This is sometimes referred to as the ghost of Jupiter. And the reason for that is that it is approximately the same size as Saturn. That doesn't. I checked, actually. I thought maybe it would be the same size as Jupiter. It's not, but it's better marketing to say that you are like the bigger planet. Actually, through your telescope, you will see it as a little softly glowing bluish disk. And it does kind of look like a dim little planet shape. That's how they got their names. It's actually a gas cloud blown off by a dying star. Next picture, please. Looking down around the rest of the constellation, most of you will be in town for something else, meaning if you're passing through here with a telescope, I know what you're doing. You're up near Corvus the Crow, just above it, looking at M104, the famous Sombrero Galaxy. It's on every kid's lunchbox. Trust me, you know this one. Yeah, right. But it is a very famous galaxy, and you're often in the area. But if you drop down lower on the other side of Corvus, you will find M68, a globular star cluster that also often gets overlooked. And then finally, rounding out the collection all the way there at the end, M83 is a beautiful face-on spiral galaxy that I'll show a picture of in just a moment. I should point out, for the adventurous and the daring who wish to go beyond this, to push this hobby to its exciting limit, drop down below that even further, you will be in the constellation of Centaurus, where you could hunt for the Omega Centauri globular star cluster, which is incredible. Centaurus A, active galaxy, all kinds of other things are just a little bit off the bottom of this screen. So if you do Hydra, don't forget to try dropping down, get brave, and go into Centaurus. Picture, please. This is M68, which is a lovely collection of stars or some dandruff or whatever you want to call it. I love these globular star clusters. I think they're really pretty. Next picture, please. We'll finish up here with M83 and Hydra, a beautiful face-on spiral galaxy, which I strongly recommend to you. Again, this is only 4 objects. There are a number more for you serious people with large telescopes. There are many galaxies through this constellation, which are well worth hunting for. Next picture, please. Just to remind you, this snaky pattern is all the way across the bottom of your southern horizon. Round about 9 o'clock, you can start seeing these stars, but around midnight, you can see all of them. One last picture to say goodbye. Until next time, clear skies. Thank you. And I'm glad to have taken up all the technical difficulties we will have this evening occurred during my segment. You're welcome. Thank you.
Thank you very much, Chris. What a fascinating presentation. And thanks for taking the toll of all the difficulties and problems we encountered. Our speaker tonight received his PhD from the Pennsylvania State University, studying ultra-cold Fermi gases, and held a NEAST postdoctoral position at the University of Colorado, developing high-precision optical lattice clocks. He specializes in developing light pulse atom interferometers and optical atomic clocks, and their applications to both fundamental and applied physics in space. He currently serves as project scientist and a principal investigator for NASA's Cold Atom Lab, a multi-user facility operating on the ISS dedicated to the study of quantum gases in space. Please join me in welcoming Dr. Jason Williams.
Okay. Yeah, thank you very much, Reza, for inviting me, and appreciate that. Okay, great. And yeah, I have to say, what's up? What an amazing presentation, and giving away a telescope. These are hard acts to follow, I'm just going to say. But okay. Yeah. All right. Yeah, I guess I can run them, and then if I run into problems, I'll drag you over. All right. Thanks a lot.
Okay.
Excellent. Okay.
Doc, you're not sharing the screen, by the way.
All right. Well, I'll call you in. Yeah, so today I'm going to talk about NASA's Cold Atom Lab. This is a facility that has been up on the International Space Station since about 2018. It is the world's first multi-user facility for studying ultra-cold quantum gases in space. Now, a number of times throughout this presentation, you're going to ask yourself, what does this have to do with astronomy? Just wait, I'll get there, I promise. First, we're going to take a little bit of a tour through my history in JPL, brief tour of quantum mechanics, and some of the cool things that are there, because that's what you really need to understand when we're talking about cold atoms. Does that work? Okay.
Yeah, all good.
Great. Yeah, go ahead and go to the next slide. Yeah, because that's really what we're talking about. We're talking about cold atoms. It's great to get things cold, but we're not just forming a big refrigerator. We've developed an instrument that studies quantum mechanics in space, quantum matter in particular. So I'll tell you about that. So yeah, I got a pretty good introduction. Could you go back up one more? Okay, yeah, I got a really great introduction. I was born and raised in Idaho. I did my graduate at Penn State and then came back to Colorado to study clocks, ultra high precision clocks, which are actually really interesting. At this point, we can make clocks that are so precise that if you lift them by about a centimeter, time is different due to the gravitational redshift. And so you're getting to a point where to define time, you also have to say, like, am I standing on my tiptoes or not, basically. So from there, went to Jet Propulsion Lab, and I've been working ever since there on the Cold Atom Lab instrument, building that up. And then you see a picture of me and my son on a recent rocket launch. That's one of the great things about having something on the International Space Station is you get to go watch it launch. And so that was a great time. Go ahead to the next slide. Many of you probably know about Jet Propulsion Lab. It's a really great place to work, I should say, and I really encourage visits. We're even still talking about the Voyager mission that's being supported there, which has such great history to it. Over 144 missions to date. We visited all the planets, and I squeezed in a little picture of Europa Clipper along with the Juno mission and Voyager, and of course the Mars program is very large. To the next. All right, great. Yeah, I already talked about this, what we're going to talk about, so you can go to the next. All right. Very quick introduction to quantum mechanics. Quantum mechanics is all about waves. It says that matter has a particle-like and a wave-like nature. And so when we talk about waves, for any of those that go fishing all the time, like I do when I'm back in Idaho, you throw a bobber in the water, makes ripples that spread out in a wave, series of peaks and troughs that spread out. If two people stand next to you or stand next to each other and both throw in their bobbers, not only are they really annoyed with each other because they're disturbing all the fish in the area, but the waves spread out and they start to interact with each other. You get constructive interference where two crests join up and they'll be big, or destructive interference where a crest and a trough, a peak and a min, line up and you get nothing. And you can get some pretty complicated interference patterns, as you see in this picture. Go ahead to the next. Young's double slit experiment showed that light also behaves as a wave. When you send light, particularly I'll say laser light, through a slit, it spreads out. And if you have two slits, each is serves as a sort of a source, and the two waves spread out, and you can see that it's a wave in this series of stripes that you see on a screen when you take a picture of the light. You'll get this. Oh, you keep losing me? Oh, okay. All right. So hopefully that's better. Apologies. Okay. Yeah, so light is waves. The main signature of these waves is when you look at the light after it's passed through two slits on a screen. There's a series of light, dark, light, dark, light, dark patterns. That's the interference pattern that you see. Around 100 years ago, then this experiment was done with matter. If you send electrons through a slit, one at a time, pop, 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 right? They will make a spot on the screen. That's the particle nature of matter. But next slide, if you will. Turns out that if you keep sending one electron through through a system with two slits, one at a time, you build up this interference pattern as well. And what this means is that doesn't come from two electrons going through the slits and interfering with themselves. That means each electron somehow went through both slits, came out and interfered with itself to make this interference pattern. Hence, matter itself has a wave-like character, a wave function, and that is what we're studying. Go to the next slide. There's also some quantum mechanics is really cool. I love it. That's why I got into this field. Properties like atoms can actually travel through a barrier. So you can imagine if you took a ball and threw it at the wall, most of the times it would bounce back, but once in many, many ages of the universe, that ball is going to go straight through the wall. We don't see that very often with larger matter, but with atoms, that happens all the time. And this is actually the reason that the sun shines. It requires this tunneling for fusion to occur. To the next slide. There's also the Heisenberg uncertainty principle. And we're actually in the International Year of Quantum. It's been 100 years since Heisenberg pronounced that the position and momentum of an atom cannot be determined simultaneous with absolute accuracy. Essentially, these are complementary properties. If you know exactly where an atom is, where it's traveling is completely unknown. Or conversely, if I know exactly the velocity of an atom, it could be anywhere in the universe. You just cannot know these two things exactly. And this is a set of complementary properties. Position and momentum, that's the position and velocity. Spin, atoms have spin, and knowing spins exactly along two directions has uncertainty. And energy and time, you cannot know energy and time perfectly. And I'm going to leave that up to a thought experiment for us all to understand what uncertain time actually means. Slide. Okay, so what we're actually studying most in Cold Atom Lab is the Schrodinger's cat, the atomic form of the Schrodinger's cat. So for those of you that don't know this paradox, this was a thought experiment between devised by Schrodinger that says if I if quantum mechanics is on a large scale, it probably happens with a cat. And so if I have a cat and I put it in a box, and inside this box I also put a vial of very deadly toxic chemicals that's all sealed up. However, there's a bobber above this vial, and if a radioactive element decays, then it'll drop the bobber, break the vial, the cat will be dead. If it doesn't decay, the cat will be alive. Now, if I close up this box and wait for half-life, that's the time that in which you have a 50-50 chance if the element is decayed or not. You don't know if the element's decayed. The cat could be either a dead or alive, 50-50 probability in that time, but quantum mechanics says it's both. It's both dead and alive until you actually open the box, see a very relieved cat that it's not dead, that scurries out and runs away. So these are all, sounds like a really fun thought experiment, but the really wild thing is that we study this, we produce this every day in the lab in the form of atom interferometry. And the idea there is that lasers can be used to actually give a momentum kick to atoms. And so, so if I have an atom and I shine a laser on, sure, it can kick an atom, or it can not kick an atom, or I can shine it on for just long enough that there's a 50-50 chance of whether the laser gave the atom a kick or not. If you do that, it turns out that each atom, again, both gets a kick and doesn't get a kick, and you allow these superposition states to separate, add another laser pulse in the middle to recombine them, and then a third pulse at the end. And what you find is that each atom interferes with itself in a atom interferometer, which is sort of the matter wave analog to optical interferometers, which are extremely precise tools and are actually at the core of gravity wave detectors at LIGO, for example. Okay, next slide. Also, entanglement is sort of the many-body analog to that. You can set up a system where you have two particles that you don't know the state of either particle, but you know the two particles have to be tied together in some way. So say one of the balls goes left and one of the balls goes right. You don't know which is which, but you know they have to be separated. This is entanglement, and those two systems will remain in unknown states but tied until you do a measurement. This is actually the key to quantum computing. You could figure that essentially instead of two balls, you have this massive network of entangled systems that can produce a network to have extremely efficient calculations that are being built up in companies worldwide, such as IBM. All right, thank you. So like we say, we're talking about the cold atom lab. It's great to get things cold, especially we're cooling gases. So when we talk about hot in terms of gas, it's basically fast particles that are not very dense. Cold gas is slower particles that are dense, and there's some very easy equations for an ideal gas that ties these together in terms of how the temperature corresponds to speed and also pressure and volume that it's in the chamber. If we look at some speed scales of things in the universe, could look at the speed of a bullet, about 2,000 miles an hour. That's actually pretty close to a fighter jet and slower than the ISS is going, but that's about the scale that air molecules are moving around in our environment. And of course, fastest man-made object around the sun is 400,000 miles an hour, which is pretty fast. If we go on the other side, we're cooling things down. Humans are pretty fast. You can get a pretty fast snail at about 0.03 miles per hour. The atoms that we're cooling down in the cold atom lab are traveling at about 10 to the -4 miles per hour. So these are actually right around the order of 100 microns per second. So hair scale, much, much colder than what you see on Earth. So it's great to cool things, but Louis de Broglie, also about 100 years ago, showed that there's this amazing relationship between how fast something is going, its mass, and the wavelength that it has. This is that wave-like character that I was talking about. And the thing that I really love about this equation is that it's essentially an equal sign. It doesn't matter if you have rubidium, which is the type of atoms that we're studying, or a electron, or an elephant. As long as it satisfies this relationship, it'll have a wavelength that's at about that size. Next slide, if you will. This was absolutely key to understanding why electrons don't decay in an atom. And like I said, even the Earth has a wavelength that's around 10 to the minus 65 meters. Very small wavelength for the Earth. That's the important thing here, is that as things get colder and less mass, the wavelength actually grows. Next slide. Next slide, if you would. Okay, so the key. All right, thanks. This is a really key of what I want to show you why we're doing this. If you think of temperature scales that we see in the natural universe, anywhere from black body radiation, which is around a Kelvin, up to the scales of, say, center of a star. You're scaling about 6 or 7 orders of magnitude from 1 Kelvin to 10 to the 7, something like that. The wavelengths of atoms, or those scales, are at about the size of electron orbitals for atoms, or smaller. And so all of the wave-like nature that you'll see is really tied to about the physical sizes of the internal structure of the atoms that we know about, electron orbitals or smaller. In the Cold Atom Lab, we're cooling rubidium atoms down to order of 100 picokelvin. So this is about 12 orders of magnitude lower than what you get the temperature of black body radiation in space, which is roughly the coldest something can get in space. At that scale, we have single atoms with the wavelengths that are tens of microns, 100, tens of micron scale. So we have a single atom whose wave-like character is on the scale of a human hair. These wavelengths are much, much larger than any internal structure of the atom. And so we are using cooling as a telescope to expand any possible quantum physics that we can explore. Next slide. And we found that you can really do this best in space. I'll explain to you why. One of the interesting things is that in the late 90s, and then an explosion of research in the early 2000s all the way to today, found that if you cool atoms down to a point where these de Broglie waves, these wave packets, start to overlap each other, a new state of matter forms called a Bose-Einstein condensate. Basically, the waves overlap, and then there's a phase transition where they all gel into a single state, a single wave, single macroscopic wave that, again, is a system that's highly dominated by quantum mechanics. And so that is a artist representation from simulation that you see on the left, but the right is actually data an atom or a Bose-Einstein condensate that was allowed to collapse and made a so-called Bosanova, where it explodes out. These have a lot of not only fundamental studies of a new state of matter, but analogs to actually high energy physical phenomena and cosmological phenomena. Next slide. And then this is a summary. I'm not going to go through all of this. It's just a very nice map of quantum physics if you want to see how it to our daily life. Thing I wanted to point out is that already we have a lot of technologies that are absolutely determined by quantum mechanics. Lasers were discovered after lots of quantum mechanics were figured out. MRIs. Superconducting devices are starting to come up, and there's even biological phenomena that's they're starting to find are dependent on quantum mechanics, such as this superposition. There's certain processes for bird tracking, sense of smell, things like that, that seem like they actually are dependent on quantum phenomena. But we're starting to learn this is actually very important to making new devices, exploring our universe, and understanding life as we know it. Next slide. Okay, so many years ago, I'll probably say decades ago at this point, it was realized that going to space is one of the ideal ways to study ultra cold atoms. In fact, that's what got me in this. I was in grad school and I saw people were making Bose-Einstein condensates and dropping them in giant drop towers. And I had no idea why you would do something like that as a graduate student. So I looked into it and found that there's new phenomena and new regimes that you can get into. Gravity is a significant perturbing force for getting ultra low temperatures, and also developing high precision sensors. And that's one thing that I forgot to mention. Atom interferometers are a cool phenomena, but it turns out that they can be one of the most sensitive sensors for gravity and gravity-like forces. It's expected that in the future, we'll be using these in space on spacecraft and in missions for position and navigation, because they're expected in the future to have better precision than what we can get with classical means. Oh, yeah, the only thing that I wanted to say here is if you look at the lower right, that's why people are developing drop towers and dropping these things. 100-meter drop tower in Germany is shown here. It's done a lot of research with atoms. They're actually making a 100-meter drop tower near Fermilab at a mine shaft to drop atoms as far as you go. But as you know, since gravity, atoms accelerate and travel at time squared. So if you want to go from, say, seconds, 10 seconds, even 100 seconds, where you just have a single Bose-Einstein condensate that you release and interrogate in space, you're going to have to go into space, because we're not going to be making 10 to 100-kilometer drop towers on the Earth. Slide. Okay, so that's where Cold Atom Lab came from. It's a first of its kind. That's what I want to say. Here, first studies of Bose-Einstein condensates in orbit, and we've done a lot of experiments in it with really the charter of what new physics can you study. Next slide. The ISS has been a really cool platform to work with. I have to tell you, what a cool lab that is. It's about the size of a football field. Yeah, and it's there are many experiments on there. It's got all the facilities of a full-fledged lab, which is what we need. These quantum instruments or ultra-cold atom experiments are not easy to put together, but plenty of power, water cooling, telemetry, and notably the astronaut crew that's helped us out. There's been about 3,000 research campaigns on the ISS, and I just want to point out that picture of the atoms there, that we're proud to say that we're basically the only ones that are studying quantum mechanics with ultra-cold atoms on there. Next slide. Been in extended microgravity for a long time, hundreds and hundreds of days. I want to point out Christina Koch, because she was one of the ones that did an upgrade for our instrument. You can see here they're carrying one of the science modules for the Cold Atom Lab. And she's an amazing person. I got to meet her, and all the astronauts are next level. I'm just going to say that. Yeah. So how do you make ultra cold atoms? First thing we need is a ultra high vacuum system on the order of 10 to the minus 10 torr. So on the order of 10 orders of magnitude or so lower than atmosphere. We need a vacuum good enough so that a background atom will not collide with your atoms on the times of a second to 10 seconds. And that is a really low vacuum. And so compact vacuum chamber is what you see at the left. At the bottom of that, we have bottom of the chamber is a so-called source cell. We have two dispensers. They're basically filaments that you run current through, and they release rubidium atoms and potassium atoms that are very hot to begin with. So we just make a gas, but then we use laser cooling. Another thing that got me into the field. This is where you can send laser beams into atoms, and instead of heating them, which lasers, as far as I knew, before getting into the field, always just heated things or welded or whatever, we use them to cool the atoms down. You can actually have, as I was mentioning before, lasers can give kicks to atoms. And you can set up a configuration where your lasers are counter-propagating. So no matter which direction your atoms move, they get a kick in the opposite direction. They get a photon kick. So they feel like they're in honey, basically, or some molasses, and they get slowed down from room temperature down to millikelvin. And then what earned the Nobel Prize for getting Bose-Einstein condensates is evaporative cooling. This is where you take the atoms. There's a certain limit you can get with lasers of how cool you can get. So you load them into a trap, and you simply sweep away the hottest atoms. It's actually how we cool down our cups of coffee or tea in the morning. You just blow across it. Evaporative cooling is an extremely efficient cooling technique, and that can get us down to around 10 to the minus 9 or nanokelvin. And then in space, there are certain cooling techniques that are more enabled or benefited. Decompression cooling. It's like why your spray can gets cold when you spray air out of it. Rapid pressure change. Here we can relax our traps, and you can cool from the nanokelvin down to 10 to the minus 10 or below temperatures. And this works really well in space. Next slide. Okay, so this is what a cold atom lab looks like in the lab. And our charter was to get something like this into something that fits in the ISS. Next slide. And that's what we did. So we compacted all of that stuff into a box about the size of a mini fridge on its side. So that's what is required to fit inside these so-called express rack that they have on the ISS. And we're in the US Destiny module, pretty close to the center of mass. It's a great system. So what's shown here is a Russian nesting doll of what's inside the instrument. I'm not going to go into it all, but the thing that I really want to point out is that the physics package is shown to the far right. It's our vacuum system. At the very top of that vacuum system is a atom chip. It has the thickness of an eggshell, and that's what holding the entire vacuum together. And you see to the left is the rocket that that this was launched from Kennedy, Florida. And I was feeling really good about our delivery until I got there and saw the rocket launch and realized that I'm miles away, something like 3 miles away from the rocket, and car alarms are going off next to me because of how much sound and vibration you got. And it's a humbling moment, but anyway, this launch of 2018, the instrument got up there and checked out and everything's fine. And so with that, we've been running science with it since. Next slide, if you will. We also have used these technologies to mature our labs. So even our labs on ground are much more simple than what you see in academia now, benefiting from this miniaturization. Next slide. Okay, we communicate to the instrument through the TDRS satellites. The ISS has real-time, almost continuous communications, which is really crazy because we can make a Bose-Einstein condensate when the ISS is anywhere around the Earth. And the really interesting thing is that we remote desktop into our computers, into the computer on the ISS to command and press, command the instruments and press go button, for example, in real time. You would think that there would be significant lag with all the signals that has to go from JPL through Huntsville, through the TDRS satellite constellation to the ISS, but there's less than a second lag. So we can move our cursors around and you don't see any problems with that. And yes, we make Bose-Einstein condensates in real time, take pictures of them. That's what you see in the lower right, which is essentially, this is a bimodal distribution. You have a thermal gas that's pretty hot, and then from that, a peak of atoms that are very cold, very contained. That is the signature of a Bose-Einstein condensate. And we do that hundreds of times a day. Next slide. This was our first paper that came out in 2020, making Bose-Einstein condensates, very robust BECs. We've made over 100,000 Bose-Einstein condensates in space as of now. So this has been really demonstrated as a very robust system. And we also showed that we could let the gas go and it expands for about a second. And from that, we got cover of nature with my favorite picture ever of an astronaut finding a BEC in space that they made. It's really great. Next slide. So in Cal, we're essentially studying three things. Like Ant-Man here, trying to understand the quantum realm, developing quantum technologies. As I mentioned, atom interferometers are extremely precise and sensitive force sensors to understand gravity or other forces. Clocks are also use similar technologies to understand time very sensitively. And you can arrange these atoms to study other phenomena that's not as controllable as your ultra-cold atoms. Next slide. One of our PIs, Nathan Lundblad, is studying Bose-Einstein condensates in bubble geometries. They have a trap that's a shell-shaped trap. And if you try to shove a Bose-Einstein condensate in that on Earth, it just drops to the bottom. It doesn't fill the whole shell. In space, it does fill the whole shell, and the interesting thing is there is a Bose-Einstein condensate is a giant wave. So it has to match all the boundary conditions. You have to have this very nice wave that matches up all around the shell, and you can perturb it, and it doesn't spin like you'd expect normal matter to. It creates vortices and a lot of new physics, especially trying to understand quantum matter on curved spacetime is one of the simulations that they're doing. Next slide. Eric Cornell is actually his team. Eric Cornell is one of two Nobel laureates who got the Nobel Prize for creating the first Bose-Einstein condensate on Earth. So we're very happy to have him on and his expertise on our team. He's now going to space to study the quantum three-body problem. And for those of you who've watched the Netflix show, the three-body problem, you know, that can be complicated. The quantum three-body problem can also be very complicated, but it's a very interesting problem. Slide. Cass Sackett is basically on the path to controlled matter and how cold can we go. And he's one of the ones that helped us get to these very low 100 picokelvin temperatures. Next slide. Nick Bigelow's team is then studying, okay, so atom interferometers are very, oh, sorry, I want to point out Wolfgang Ketterle, who's on his team, who's the other Nobel laureate who got the Nobel Prize for making Bose-Einstein condensates. And we're also very happy to have him and his expertise. But Nick Bigelow's team are all interested in atom interferometry, which I mentioned are very precise force sensors, especially sensing gravity. So the idea here is that tests of Einstein's equivalence principle, or I should say the universality of free fall, are really, really telling because, or could be really telling because that universality of free fall is the key to one of the major keys to Einstein's laws. No test has found any violation of the universality of free fall anywhere from apples and feathers all the way down to recent microscope mission in space that tested this down to about 10 to the minus 15 level. Atom interferometers have quantum matter though, wave-like matter. And there are different things and different phenomena that might pop up when you're looking at how does a wave behave in gravity in a gravitational field compared to classical matter where the wave is so small. Next slide. And then my team are studying forming molecules. These are some of the largest molecules that you can create. Essentially, if the atoms weren't ultra cold, they wouldn't be this large. They're as large as their de Broglie wavelengths are. And so we are forming molecules that can be as big as bacteria, made out of two atoms, for example, and studying them, using them for a source for sensors in the future. Next slide. Okay, so our achievements, hundreds of thousands BECs really demonstrated this technology in a very controlled manner. We've demonstrated dual species BEC, so that's rubidium and potassium gases that make a BEC simultaneously, and we saw mixing, actually repulsive mixing, non-mixing, oil and water type of phenomena in these two gases on space. Nick Bigelow's team has demonstrated delta K cooling down to 52 picokelvin now, and that's first attempt. He's now trying to go lower and lower. Next generation, we're hoping to get around 10 picokelvin. There's no, well, the limit of how cold you can go is basically how big is your vacuum system. So there's future ideas to go down to femtokelvin and then create atoms in free space where you don't have a vacuum system and just make a single wave functions centimeter side, you know, large as you can go. Also, we've demonstrated single species and dual species atom interferometry. And next slide. Okay, so I have results from atom interferometry. I'm going to go through these quickly because I know we're getting late, but I already mentioned atom interferometers are the analog to optical interferometers. Next slide. And how you implement them how we did in Cold Atom Lab is with a simple laser beam. For the first science module, which holds the vacuum system, we did not have an atom interferometer in that. It's actually about 2 years later, we sent up a new vacuum system that had the atom interferometer capabilities. And we achieved that by this module you see on the top, atom interferometer platform, where you send a laser beam down and retroreflect itself. Just that tool, and then some very complicated ways to control the frequency of that tool, makes a, when you send a laser beam down and reflect it back on itself, it interferes and it makes a grating. And basically it's that grating that the atoms reflect off of and get kicks or not. We've used that a number of ways. One is we used it to sense vibrations of the on the ISS. And if you look in the lower right, this is where Cold Atom Lab is. And you'll see right next to it is the exercise bike, which is pretty funny because we're testing one of the most precise force sensors that you can have. And so we did some initial experiments, saw not when the guy was running the bike, but we could sense and characterize vibrations from the ISS. Next slide. And then also, so this is a really cool experiment where with a single laser pulse, you can see interference fringes in a single cloud. So you can do a single measurement with a cloud of atoms and get a lot of data about the force and gradients and things like that. This is building up towards a force sensor for applications for navigation for the future. Next slide. And this is preliminary or first results from dual species atom interferometer, where essentially, if you look in the lower right, if you map the output of each atom interferometer, they should be perfectly lined up. If they're not perfectly lined up, you either have systematics like we did in this data, or if they're not perfectly lined up and these waves are shifted slightly, then that is what you'd look for a violation of the equivalence principle. But we're not at the sensitivity yet to be looking for that. Next slide. So up one, I think this one. Oh no, okay, down one. And then finally, Nick Bigelow's team has shown a differential atom interferometer. That is where you take a single cloud and you separate it out initially, and then you run 2 atom interferometers simultaneously. And this is great because now you have a lot of common mode noise rejection. Essentially, you only see effects that are different between the 2 clouds. So if somebody's even writing on that exercise bucket, it doesn't matter. What would matter is if gravity works differently between these two clouds, up and down. And it's this is a technology that's being matured for mapping the Earth's gravity. Right now, state of the art is from this Grace and Grace follow-on mission, where two spacecrafts are separated and do laser ranging between them. So if there's a mountain or something, one of the spacecrafts gets pulled a little bit more than the other, and you can map out the Earth's geode, which is what you see down in the left. That's actually the map of gravity, which is very different than what the actual map of the Earth looks like. This technology, there's a mission concept being built up at JPL to do the same sort of mapping with an atom interferometer using this differential technique. Both in space and on ground, you can see a lot of phenomena: subsurface water, tunnels, et cetera, et cetera. This is technology. Next slide. Okay, so here's one of the bigger questions. Why are we doing this? Why do you care about quantum mechanics at all? And I think the answer is that we know that there's a lot we don't know about. If we just look at general relativity and quantum mechanics or quantum field theory, there are things that we don't know how they hold together, and there are things that we know that they don't hold together completely. There's certain the physics around a black hole, for example, is not well jived, and we do not have a stable working definition of whether gravity can be smooth or if there's a quantum aspect to it. Some things to think through. Yes, as I say, is space-time smooth? General relativity is sort of based on that. It says yes, it is. Quantum field theory. The closer and closer you look at the vacuum of space, you get these quantum fluctuations where matter appears and disappears all the time. And the two haven't been meshed into one theory yet. Also, the description of time, general relativity, of course, it's a great description of time, mind-blowing description of time. If you think about, you have an atom in a superposition that's traveling where there's two states traveling two paths at the same time. What does that mean for the time that that atom actually sees and when it recombines? There's open questions there. Gravitational field also, of course, general relativity explains that at a very high level, but what is the gravity, or how does the atom in a wave packet experience gravity? What does that actually mean? If I have this wave packet that's highly delocalized in a gravity gradient, are you actually going to see tidal effects on the atom itself? It actually gives some questions as to localization of the atoms and yeah, what that actually means, a wave packet in space-time. Next slide. And dark matter and dark energy also, some of the biggest unknowns of our time. We, as it stands right now, we only understand about 5% of the visible universe. Atom interferometer, or atoms, ultra-cold atoms, can provide unique sensors to try to look for local signatures of dark matter and dark energy. Some papers that came out about a decade ago where instead of doing astronomical observation to try to understand dark matter and dark energy, ultra precise sensors can actually be placed in, say, low Earth orbit, and you can try to look for these forces that go beyond gravity locally. Unique experiments that can then be tied to astronomical data. And that is really why we're doing these research, to answer fundamental physics and try to contribute to these big unknowns of the universe. Next slide. Next slide. We're doing great. I wanted to show you, we're always happy to have people get involved with Cold Atom Lab, and there's a cool picture of a Bose-Einstein condensate superatom right there that we like to take. If anybody's interested in opportunities or wants to know more, get a hold of me. There's my email, or you can go to just coldatomlab.jpl.nasa.gov. I'm happy to talk more. Next slide. Next slide, if you will. There's a lot of quantum and popular culture. Two things I wanted to point out is Ethan Elliott leads our EM testbed, and he had a chance to do an interview with Ant-Man a couple of years ago, which is really great to check out. And also, if you've seen Constellation show on Apple TV, it's basically the show where Cold Atom Lab, that they call out there, somehow malfunctions, destroys the International Space Station, perturbs the lives of the astronauts. I'm not going to give it all away, but it's a great show, except for seeing our instrument destroy the International Space Station was a little bit stressful. I've got to tell you that. Okay, next slide. I think that's and then here's a nice video also you can look up on YouTube that's great for kids to try to explain what we're doing. Slide. And I think that's basically it. In summary, I went through why we're interested in the Cold Atom Lab. This year is actually UNESCO's International Year of Quantum, and so there's a lot of activities related to quantum mechanics that's going to be going on throughout the year, and NASA's is going to be added to the National Quantum Initiative, or is added to the National Quantum Initiative now too. Next slide. And yeah, I want to thank you all for your attention. And this is the team. Of course, I thank the team of who worked on the Cold Atom Lab. To the left, man to the very far left, Kamalo Dreer is our program manager, and then the teams of principal investigators to the right. So thank you all very much.
Yeah, I can take a question.
All right, great. Thank you. Cool. And thank you very much for running that. That worked out really well.
We have questions here. Yes, sir.
I appreciate that. Yeah. Okay. So that was that. Yeah, that was a very, very good question. There's been some recent time delayed entanglement experiments that have been achieved in the past, and the question is, with some of these experiments, has shown that that phenomena in the present and time delay experiments can affect things in the past. And how does that actually start to play into the cold atom lab? How does time even play in when we're starting to get into this regime where, how did you say it, sir? Time is just it's just an anomaly. I like that. Yeah, I like that a lot. That is a very good one. So I think this all comes into if we go back to Heisenberg, one of my favorite guys, his uncertainty principle, which talks about if I know the velocity of a particle perfectly, it could be anywhere in the universe, right? One of those complementary properties was energy and time that I told you about before. And this is really telling that time is uncertain in certain scales, in certain energy scales. And so how that relates to the cold atom lab, we haven't gotten into these scales yet, but with atom interferometry, to some extent, there's a there's a region of uncertainty where you around in time and in space around these atoms that you just cannot know. Basically, you can't pinpoint it down. You can't know at what time something happened due to quantum mechanical uncertainty to high enough precision. And then as these quantum effects grow, as your energy drops, your time uncertainty grows, and it gets more and more impactful for us. Clocks. So I did my postdoc work with clocks. Clocks are going to be a different instrument. You need to use strontium. So yes, clocks. I should be careful because I talk about this too often. And I'm sorry. The question was, are your clocks related to Cal or used in Cal? We have the atom interferometer tool in the cold atom lab. We can make a rubidium clock in the cold atom lab. But there's a new generation of clocks called optical atomic clocks that basically uses the frequency of a laser as their tick rate. And these can be extremely precise clocks. These are the ones that I was telling you about that can now know a second to 18-digit points. And that's where the new physics comes in. You need a new type of atom, strontium, that we don't have on the cold atom lab. It's conceived as a next generation Cal that we'll start to, or that we're looking to. We do not use rubidium clocks on. Yeah. We don't use those in cold atom lab because that's actually a absolutely mature technology right now. That is a type of clock that is used in the industry as a standard timekeeper. Yeah, for sure.
Yeah. Are you asking for, Barbara, we don't have your sound, but if you're giving us airtime, yes, we do have quite a couple of questions online.
Yeah, we've had a couple questions here. So why don't we take some of the online ones?
Yeah, sure. So the first question is that, would you elaborate more on the process of miniaturizing your lab into a box? And as we understand, they're very delicate instruments there. How did you, let's say, shake-proof them as you described, and how shaky a launch is?
Yep, shake and bake. So Cold Atom Lab was on an accelerated schedule. So I should mention that it's a Class D mission, which allows us to accept a lot of risk for something new, which is great. So a lot of the work of miniaturization work was on two tiers. Half of it was done with companies, and one of the big innovations was that vacuum chamber, which is about the top cell is about 1 inch on a side by 2 inches long. That compares to basically these like 15-inch vacuum systems that can take up a half of a table. So that was all matured by a company in Colorado inflection or cold quanta. And that was an enabling part for us to start. But then we just had to miniaturize everything else, including the lasers, the electronics, the control systems to lock our lasers. And that all went fine. It's interesting. One of the most difficult things is you can miniaturize everything, but once you put it all together, shove it together, it starts interacting with each other and makes it much less stable. So anyway, that was a multi-year campaign. The team at JPL did all of our electronics, and we're lucky to work with them because they actually do know how to miniaturize and how to make very good electronics. So I would say that that was enabling. After we had everything ready and in a box, we had to go through an environmental campaign. So as Reza had mentioned, we shake it. We put it on a shake table, and you shake it at, it was not what's so-called workmanship, at which if I were sitting on the table, I would be shook to pieces, basically. But we launch on SpaceX in foam. And so we launched to about those levels along all three axes for quite a while, hours, just to make sure it'll survive launch. So we did a simulated launch. We put it in an oven, the whole thing in an oven while it's operating, and took it between 5 degrees and 50 degrees C. Not because that's the launch environment that it was going to see, but in case you're driving through a snowstorm in Colorado and accidentally hit a heat wave in the Mojave Desert, it'll survive whatever environment it'll take to get there. And then we did EMI EMC. Because we're on the International Space Station, we cannot make signals that will perturb other experiments. And we actually did have a lot of radio frequency and microwave fields that we were emitting. And so we put it in a room with sound cones that just sensed what it was doing while we were operating. And that was primarily the environmental campaign.
That's great. Let's ask another question before we go into in-person audience. You mentioned that you had remote desktop access. You have remote desktop access, and it's pretty not laggy. 1 second just delay. That's great.
Right.
So, first of all, how do you manage the time? You mentioned a couple of teams that you're working on that lab. So, how do you manage the time? Who gets when? And then are you affected by the periods of signal loss that the International Space Station experiences?
Yeah, so let me ask the second question again. You said, how do we handle signal loss?
Yes.
Okay. All right. Yes. So the teams are all great friends, luckily. That's a very important thing. There's five PIs, and then they each have anywhere from 2 to 20 students, and that we actually have some co-investigators in Germany as well. So it's a pretty extended team, and they're all some of the best people that I've ever met in my life. How we coordinate it is two-tiered. There are things that we all need to know, and we all co-decide on campaigns in weekly meetings. There's things like, do I have a background magnetic field? We all coordinate those experiments and then run them. But then there are individual PIs or individual runs, and the PIs basically get equal time. We run experiments for 2 PIs a day, and then we just cycle through the PIs throughout about a week. And that works out pretty well. Now, where the tables come from, actually the team at JPL gets the instructions that are boiled down to a very high level and then translates those into tables that can be run on the flight instrument. And then we coordinate it, we schedule everything. As project scientists, I sort of coordinate what will be run for the day. But we have 2 operators that are available either in the EOMOC or operating somewhere remote. EOMOC, Earth Orbiting Mission Operations Center at JPL. It's a cool building, cool room. And they have a checklist for the day. I'm going to run through basically. So it's all scheduled out in advance. Signal loss is a great question because we have TDRS satellites, but there's a handoff. So we can have coverage anywhere between an hour and a half and 5 minutes. There's little gaps. And then between there will be gaps that are probably 5 to 30 minutes. And rarely the ISS will tell you, I just need you to shut down right now because we've got something else that we need communications for or something else. And so these are all scheduled. These are all sort of batched up. The operators just run the experiments. And then when we don't have coverage, we tell the instrument to go and you stand back and you hope it all worked out well for that 20 minutes and you come back and you get your data.
Okay, great. And you mentioned your relationship with the ISS operators. So if I understand, you do not need to coordinate with them for everything you do on the lab, right? It's your black box. You do whatever you want unless there is some specific situation. Can you elaborate on that?
That's a great question. I'm glad you asked that, to be clear. So we have operators that are at JPL that are within our team. They are the ones who remote desktop into the instrument. And we have two. We have an operator that's running the instrument, and then we have a missions operations engineer that is listening on the so-called loop. She's listening to the chatter from the ISS team at Huntsville and answering questions. So we do not need astronauts to do anything for us except for once every, or maybe once a year or something like that, when we repair something, upgrade something, and the astronauts are actually in there repairing something. Otherwise, we don't need them actively, but we are always, or the missions operations engineer is always conscientious of what they're saying at Huntsville, what's going on with the instrument, both to listen for instructions, or if they say your water might be a little bit hotter or something like that, they can feed back to us if it affects our data. So yeah, there's a lot of coordination, like nothing I'd ever seen before coming to JPL.
Okay, great. Thank you. Let's switch to in person.
Okay. So it's about the gravity map, and were those measurements taken at the surface, and did they account for altitude? And these are the ones that were shown that had the colorful map of the Earth that did not look round at all. Yes. That is data that's extrapolated from the GRACE follow-on mission. So those were taken from the satellites, and just very minute differences in separation of the satellites. And a lot of passes around the Earth. Yeah, they could extrapolate that. Absolutely. They see a lot of like the oceans, subsurface structure. Yeah, you can get an incredible amount of information out of those maps.
The ATS-1 and 3 satellites that went up in 1963 are still up there and still operating. They're not doing video, they're doing transponder work, and they ran out of gas a long time ago. So they parked them in a geomagnetic null over New Guinea. I didn't know there was one.
How do we get a tour of JPL? Yeah, so of course, there's the public days, but there are private days. So I would recommend going to coldatomlab.jpl.nasa.gov or email jrwillia@jpl.nasa.gov. Drop me a line and see what we can do. What's that? Yeah, I'll have to get back to you on that. They used to be in the spring, and then they moved them to the heat of summer for a little while, and I don't know where they've landed now. Yeah. Oh yeah, did the creators of Constellation consult with us at all? Not at all. That was a It was actually a complete surprise to watch a show that I did not know what it was going to be about and find that out. Okay, good. Yeah, I have a feeling that's how it goes a lot of time.
Are there any other online questions?
Yes, a few. First of all, can you elaborate more on the vacuum that you mentioned? It's very high. How do you achieve that on Earth and on space? Is this just a simple vacuum pump? I guess not. Can you elaborate on that, please?
Yeah, absolutely. So I think that vacuum technology is probably one of the most important things that we as a community have developed over the last 30 to 40 years in order to enable these studies. So how they achieve a vacuum is, first of all, you have to have an exquisitely clean system. So we very often produce a system out of glass cells or out of all metal, and then you put it in an oven and you bake it out for weeks and weeks and weeks and weeks and weeks to get rid of anything that might possibly be contaminating. Then you seal it off, can pump it down to a certain point with a roughing pump, just a standard, like, I mean, oil-based pump sometimes, which is really scary, but it works out fine. And then we use ion pumps, which are running continuously. They're always on an ion pump. And ion pumps are basically this technology where you've got a plasma discharge that coupled with magnetic fields that makes these electrons or ions that are spinning, and if they see an atom, they knock it into something that captures them. And that is just running continuously all the time. And with that, we've been able to get down to the 10 to the minus 10 torr, which is effectively, yes, you get one collision with background gas every 10 seconds with your atoms. State of the art's maybe 10 to the 12, approaching 10 to the 13. And there's also, so this is one technology. Having access to space, I'd mentioned that we're thinking about possibility of making ultra-cold atoms in the free vacuum of space. There are also techniques, if you go into deep space and use wake fields, where you have a plate that basically sweeps ahead of you, you can achieve really high vacuum right behind that as it sweeps the atoms away.
Great, thank you. And can you tell us more about your own research? You mentioned you work with molecules rather than smaller particles. So are those molecules with electrons all around them and they excite and not? Can you tell us more?
Absolutely. Yeah. So the research that my team is doing is molecules that are made out of two atoms, rubidium and potassium. It's a dimer, just two atoms that are together. But the unique thing that we do is rubidium and potassium has a so-called Feshbach resonance around it, which sounds scary. But what it means is that you have, if you have two free atoms and apply a magnetic field, it can shift the energies of these atoms. Just the electrons are sensitive. The energy of the electron states are sensitive to a magnetic field. So you can actually sweep from to be so that two free atoms have the same energy as a molecular state would. And this resonance has some pretty wild properties. Basically, just because there's this resonance there, you can make it with a simple applied magnetic field so that the atoms can be extremely strongly attractive to each other or extremely strongly repulsive to each other, or no interactions. You can control how these atoms interact with just a simple magnetic field, which is really great for simulating a lot of different systems. That's how you make two BECs that are either miscible or immiscible, can mix or not mix, create lots of studies. You can also make molecules out of them. You can sweep your magnetic field, and you can go from free atoms to forming molecules coherently, which means that there's no energy lost. And there's one of the things that we are going to extend. I have to admit that this is not the first time it's ever been done, but we're going to extend it in space. Is you can do one of these sweeps, so you can make a superposition of if your molecules are, or if you have molecules, or if you have free atoms. The system is unknown whether it's in a molecule or a free atom, and it sort of oscillates in those two states, and there's unique interactions there. But the selling point for my project, why it got funded, is a preparation for an equivalence principle test. So if you think that I have rubidium and potassium gases in a gravity field, and I want to see if they fall at the same rate under gravity in Earth's field, if these two gases are separated a little bit, they're going to see different gravity because there's a gravity gradient there, right? Gravity for rubidium will be a little bit less than it is potassium on the top and bottom. You'll get an anomalous violation that's not real, and you will be mocked by the media for saying something that was not absolutely true. So it turns out if we want to start going towards or beyond the state of the art to these testing, if gravity works on rubidium and potassium at 12, 13, 14, 15 digit points, the overlap of these atoms have to be precise down to nanometer scales. You have to know exactly where the center of a 10 or 100 micron large cloud is down to sub-nanometer scales, which is really challenging. If you make molecules out of them, clear away all free atoms, these molecules are unique. They're perfectly round. They're actually in a state where there's no structure to them at all. And so you can make molecules, then separate out your molecules, and you have perfectly overlapped gases as a starting point for these tests. So.
Great, thank you very much. And follow up to that, you did mention how gravitation plays a role and electromagnetic waves you use to control them. Do the other forces, weak nuclear and a strong nuclear force, also play a role there? And the one person wants to know if you have seen any evidence of a fifth force by any chance.
Yeah, so we have not, I don't think we're at the precision where the other forces are affecting us as of yet. It is a great question because as you have these highly delocalized systems, it basically means you don't know where your nucleus is, you don't know where your electrons are within this very large packet. You have to have extremely high precision or some, I guess I should say, in order to see effects of the nuclear force, things like that, you have to have some other background field or background structure that it will be interacting with, which hints at physics beyond general relativity and the standard model that we have right now, which is what we're looking for. So it'd be great, but we have not seen any. We haven't seen effects of those. The atoms do not seem to be affected in any way. If you're looking at, if you do spectroscopy, send light in, that light's exactly the same frequency, whether it's super cold or a little bit hotter. So it doesn't affect any of that physics. Have we seen evidence of other forces, other fifth forces? That is absolutely the name of the game of what we're looking for right now. That is dark matter, dark energy. It's basically signatures of gravity-like forces for things that we can't see. And so there are searches for, a force that can't be explained by matter around. That would be a dark energy force. There's searches for fifth forces, forces that might scale differently than what you expect from matter. There's a whole class of phenomena that, when you look at ultra high precision, is expected to emerge if you believe string theory or quantum gravity, things like that. It's expected that we will see signatures of things beyond what we see right now, and that's what we're looking for. Because I mean, fundamental physics, why are we looking for these new things? If you just go back to how much has Einstein's, even special relativity, his these findings of just a very small tweak of how Newtonian physics works at incredibly high speeds that no one ever thought they would get to. It seems like just a minor tweak, but it brought in the atomic age. We can't have GPS without it. It really does affect our everyday lives, and especially at NASA, it affects everything you do. So that's what we're looking for, next generation. And I think we're at a point where everything doesn't hold together right now. General relativity, standard model, these don't all hold together. They don't explain everything, all the evidence that we have.
Thank you. That's it online for now.
Last chance. Okay, will you be around for a few minutes? Okay, so for those of us that are here, he will be here to answer questions, maybe discuss things a little further. And I think that's all from here, Raisa. Do you want to
Great.
close
So
off, or
at
do
the
you
end,
want me to?
yeah, sure. Let me first thank everybody online for their patience while we were figuring out things. And thank you all for joining us. So I would say all goodbye and great night.